GNSS satellite transmitting signals with different frequencies, structures, modulation, okay? But you have to take into account that the signals are with a very low power. It's like a bulb of power, something like 44 watts, which is just nothing. GNSS satellite transmitting signals with different frequencies, structures, modulation, okay? But you have to take into account that the signals are with a very low power. It's like a bulb of power, something like 44 watts, which is just nothing. What does it mean? That when the signals are traveling to the Earth, the signals are arriving on the noise levels, are really inside the noise levels. Then it's a huge work of the receiver later on to extract the signal from these noise levels, okay? And because, the signals are really high attenuated when they are going through the Earth, okay? Then which is the spectrum that we are addressing in the GNSS? Where of all the spectrum of frequencies, we are in the spectrum for around 1 to 1.5 gigahertz frequency, okay? What we call the Uhf spectrum, L-band spectrum. Then we are transmitting in the L-band spectrum that is covering, as you see here, different kind of frequencies for different constellations that you can see the spectrum here. Why we decided to choose the UHF spectrum? Because this minimizes the effect of the atmosphere in the signals. In particular, for example, a ionosphere in lower frequencies, they have a reflection problems, and also troposphere. Troposphere have another problems. Then at the end, we choose to have UHF or L-band frequencies to minimize these effects of the atmosphere on the signals, even though we have some effects, and we have to care about it and we have to get rid of it, but minimized or optimized, let's say. Between all these frequency bands, we have, if you see in this particular slide, you have in the top, you have the higher band, which is the traditional frequency L1. Then you have around 1575. You see the L1 in GPS and Galileo, Beidou, and GNSS, which is the blue one. This is the L1. And then we have the lower band, which is the new frequencies that are coming up since a few years ago in all the satellites, the L5, L2, and B3 of GLONASS, for example. Then we can, inside the L band, we can just make a difference between the upper band and the lower band spectrums, okay? Then the first one, let's say, is the L1, which is the traditional one. It means that, we've been working with the L1 for many, many years. That's why they are very robust in the sense that we are trying to protect for aeronautical purposes a lot, but the new frequencies, L5, L2, or X6, for example, for Galileo, they are more vulnerable in the sense that we don't have any protection today, and we were working on the protection. Let's talk about another important thing, which are the atomic clocks. If GNSS is working today, is thanks that we have in the satellites atomic clocks. What does it mean, atomic clock? It means that we have a very precise clock by trying to have very stable time in the signals, right? This, in particular, for example, usually what we have is rubidium clocks, the RAFs oscillators, or hydrogen maser clocks. In Galileo was the first time we are putting in place a hydrogen maser, a new technology in a satellite. After some problems that we had, they are behaving very good, even though some satellites they are having some instabilities. But globally, an hydrogen maser is very stable. Yet you can see the weight of these clocks here. The hydrogen maser is 18 kilos, which is very heavy, and these are the cost is very expensive. It's something like $100,000. Right? The graph you see here is a kind of the stability. I don't know if you heard about the Allen deviation. The Allen deviation is a measure of the stability of a clock. And you can see, for example, at the end, the Allen deviation is a kind of standard deviation or a covariance of different deltas of stability of a clock. Then, as you can see, for example, the red color, which is the hydrogen maser, at the end, they have much more stability than the one in the blue. That's why the hydrogen maser is better than the RAFs, the rubidiums, yes? Then thanks that we have these atomic clocks, we are able to, with this oscillator, to generate signals very precisely, very stable in time. And the first thing the signals have is what we call the carrier, okay? Then we will generate a signal carrier of a given frequency, 1575.42 megahertz, for example. This is the L1 carrier. And this carrier carry inside what we call the ranging codes or spreading codes or peering codes. This peering codes or ranging codes is a sequence of bits with no data inside, just bits with a particular sequence And this sequence is different per satellite. And the access of this signal is based on what we call CDMA, which code data access. It means that every single satellite transmits different PRN codes in order to the receiver know who is the satellite that is transmitting the signal. Then you have different sequences per satellite. Apart from knowing what is the satellite transmitting the signal, these codes are very, very important for the receiver to estimate the distance between the satellite and the receiver. Because as you will see later on, the distance between the satellite and the receiver is one of the most important information that we need in order to compute our positioning. Then the ranging code serves to two things. To know which is the satellite that is transmitting the signals, because the sequences of the PRN codes are different per satellite, and also to know receiver, which is the distance between the satellite and the receiver, what we call the pseudo distance. I will see later on. Then these ranging codes are very, very important and can be different for GPS, Galileo, and even GPS. They have different ranging codes for different frequencies, and also even in the same frequency, we can have different ranging codes for different purposes. And the other part that is very important when we are transmitting GNSS signals is the navigation message, okay? This is a data message. This is a data bits. Then we have some bits. That is, we are transmitting every 50 bits per second with information inside. Information that can be decoded from the receiver later on in order to have some information, important information for navigation inside. As you see, you have our carrier with a given frequency, which is very controlled by the oscillator of the clock. We have the ranging codes, different sequences of bits that serve to acquire, to know which is the satellite transmitting the signal, and also to know the distance between the satellite and the receiver, and also the navigation message with data information inside. The PRN codes or the ranging codes, they don't have any data information. Then at the end, if we multiplex or modulate everything, at the end we have a transmitted signal, which is modulated with these three components. And this signal is composed of a power. This have a power. We have the ranging codes inside. We have the data inside, and we have the carrier with a reference frequency. Yes, this is a signal, a GNSS signal at the end. We can complex it a little bit. For example, we have military signals that can be encrypted inside, and we have an encryption key that will be on the top of this in order not to know which are these ranging codes for other purposes, only for military purposes. But this is the most simplest way to generate a GNSS signal. An important thing, if you see the red color, is that these signals are transmitted from the what we call antenna face center of the satellite. What does it mean? Let's have a look on the screen. You have a satellite. Usually you have the solar panels. The satellite is pointing with an antenna towards the Earth in order to maximize the gain towards the Earth. This is what we call the APC, antenna face center. Then the signals are being transmitted from the antenna face center. This antenna face center will depend on the frequency, L1 for example, or L2 or L5, different frequencies. But not only the frequency, it depends on the code. And the code, or the ranging code, as you will see later on, we have in GPS we have the code CA, course acquisition code, or the P code, which is an encrypted code for military purposes. Then the antenna face center will change slightly in different points depending on the frequency we are transmitting, and also depending on the ranging code we have. For example, in the GNSS GPS plan, what we have different frequencies with different ranging codes and different modulation types. For example, the traditional one in GPS for civilian users is the L1CA. What I want you to take, the L1 code acquisition. This is the one used for civilian purposes. Then we have the traditional as well, the L2P and L1P and L2P. These are encoded with an encryption for military purposes. It means that a civilian receiver doesn't know the decryption keys and cannot decrypt these codes, and then they cannot use these frequencies or these codes for positioning. The difference between this and this is that these ranging codes are much more precise in the signal, and the positioning will be better, right, for military purposes. In the new plan for the modernization of the new satellites that are being launched in the GPS, we have also new civilian frequencies. We have L2C and L5. Okay, then these new frequencies are very good because receivers, a civilian receiver up to now, let's say so far, can only use L1CA, one frequency. But in the next generation of the GPS satellites, then now more and more they are having this three frequency transmission. We can use several frequencies, civilian usages. Then this is very interesting as well for the receiver. You will see later on why. Okay, in the Galileo plan, we have already 4 different frequencies that are civil frequencies and accessible from any receiver today. We have the E1 frequency, which is the same frequency as the L1 in the GPS, 1575.42. And depending on the service we are providing, we have different pair of frequencies. But we have the E5A, E5B, and E6. Okay, then depending on the service we are providing, we will use one frequency or other frequency with different data information inside the data. You remember the navigation method with the data inside, depending on the service we are providing different data depending on the frequency we want.